Hello everyone and welcome you all for today's discussion, today's class. Yesterday we have discussed about velocity potential, stream function and its physical significance and how velocity potential relate with the stream function. Still two, three topics remaining from kinematics of fluid that are rotational motion and vorticity and circulation. So today we have started fluid dynamics of fluid. So and Bernoulli equation, Euler's one-dimensional equation for the fluid. So first cover the dynamics of fluid, and then in 2-3 days I will also cover remaining topic of the kinematics of fluid, particularly rotational flow and the condition of vorticity, how rotational flow is integrated with the vorticity and circulation. So three important topics are still remaining, and I will cover in 2-3 lectures in next incoming before the onset of the Diwali festival. And so today we are going to start. This is one of the most important topic of the fluid dynamics, is Bernoulli equation concept of energy, because in dynamics of fluid means earlier in kinematic of fluid we have demonstrated geometrical approach of the describing fluid motion, but here we also consider how forces involve, how energy, because force and momentum is expression of the energy, because energy expresses itself with the force and momentum. So whenever there is a moving fluid, whether it is a flow from the volcanoes or flow from the river, flow from any kind of flow, always involved with the forces. So here we will consider forces, because ultimate aim of the fluid mechanics is how forces are created with the moving fluid, whether it is hands, whether it is a lifting of the aeroplane, moving of the aeroplane or helicopter, all kinds of the motion inside the fluid involved with the interaction of energy and force. That's why I want to start here first Bernoulli equation. First we describe kind of energies involved in fluid motion. So main topic is dynamics of fluid. Dynamics of fluid, dynamics of fluid, the motion of fluid in which energy, momentum, and force involved. Force also takes place, also considered. When we talk about the energy is first. Energy comes first. Due to energy, force comes in secondary, and then by force we can do work, because we know that force into displacement equal to work. So in dynamics of fluid, mainly there are so many energies: internal energy, thermal energy, heat energy. During motion of the fluid through conduit or any channel, it is generated, but we never consider internal energies, whether these are due to irreversibility, rise of entropy and generation of heat. All these energies are not considered in fluid dynamics. We consider only macro energies. Only macro energies are considered in analyzing the dynamics of fluid flow. So these energies are kinetic energy of flow, kinetic energy, and potential energy, 1 by 2 mv square, potential energy. This energy also bulk energy, mgy, and pressure energy, or you can also say pressure or flow energy. It is also known as a flow energy, that is equal to PV. Here V is taken volume. We taking cross here because we may confuse with velocity. So here we will take PV means volume. V stand for the volume. So flow energy means pressure into volume. So these are energies that we will consider during the analysis of the fluid flow and derivation of the Bernoulli equation and Euler's one-dimensional Euler's equation representing forces involved in fluid motion. So first we define what is a flow energy. Let us start defining flow energy, because this is here lot of confusion create in mind of what is a flow energy, pressure into volume, how it comes and pressure into volume. So this is any cross section. Any cross section you are taking here, some flow channel 1, 1 and 2, 2. Let us define what is a control surface and control volume. Control surface and control volume. As you know that in solid mechanics, material remains rigid and volume and mass not change while considering motion of the object. But here in fluid mechanics, material is not rigid; it is expandable. Particularly in fluid, it may expand due to changing of density. Mass will change. So we follow control surface and control volume approach. Let us define control surface. Here is a control surface. We focus on control surface here. Control surface. And let us see here, velocity is V1 and area is A1. Velocity at this point is V2 and area A2. So at time t, velocity is V1 and in a delta in this time interval, t equal to t plus t dash equal to t plus delta t dash, and it will reach here. This fluid will reach here. This fluid will reach here and traversing distance at dx1 here and dx2 here due to velocity v2 and v1 at t equal to, this is at t equal t and this is equal to t plus delta t. Initially fluid was at this position to this position and now changing, let's define with another sign, reaching here. So traversing distance dx1 in time interval delta t. So how much distance covering dx1 at 1 and dx2 at 2? So what is force? Force equal to pressure into area. We know force equal to pressure. So pressure was P1 and area was A1. And work done due to this pressure force, W1 equal to force into displacement dx1 and dx1 is equal to V1 into delta t. So V1 into delta t, dx1 is covered by fluid due to V1 into delta t. V1 is the velocity at this point. dF into dx1, that is equal to pressure P1 into A1 into dx1, and this A1 and dx1 equal to volume V1. So this equal to P1 V1. This is a pressure force. This is a pressure. This one is because you are doing work. So pressure energy, or you can say flow energy, because fluid is pushing here due to change of, because P1 is greater than P2. That's why this pressure, due to higher pressure from this side to this side, it is pushing fluid inside the conduit or inside the channel. So work is done by the pressure energy. Due to pressure, work is being done. So this is known as a pressure energy or flow energy. So this energy involved in another energy involved with potential energy. Potential energy due to position of the fluid. Potential energy because we go upward. When we raise something, a fluid is being raised at higher position. So mg will act downward, and this force is downward. So work done equal to force into displacement. Suppose y distance is moving upward. So force F into y, that is a mg into y. This energy that we doing in raising fluid upward is stored in the form of the potential energy. So that's why the fluid always have potential energy, mgy. Another energy that is I want to define due to work done, energy converted into kinetic energy. So let us again define here. Force F equal to mass into acceleration, that is equal to mass into dv by dt. We can break it m dv by ds into ds by dt. So F into ds equal to mdv into v. So mv dv. So F into ds is if we integrate this one, F into ds equal to mv dv. Integrating from f ds 1 to 2 equal to m v dv 1 to 2. That is equal to f s2 minus s1 equal to m v2 square minus v1 square by 2. So that is a work done. W equal to change in kinetic energy delta Ke. Work is done on the fluid. So kinetic energy of fluid will change. So all three energies involved in Bernoulli equation. Bernoulli equation in fact is a conservation of energy during flow of the fluid in one dimensional, steady and incompressible for ideal flow. All three energies remains constant. That is a concept that we are going to derive in today's discussion. So let us now start. This is a concept of energies that involve in today's discussion. That is Euler's equation. So let us define Euler's equation. Euler's equation. Derivation of Euler's equation. Same Euler who given Euler's approach of the analysis of fluid motion, Eulerian approach and Lagrangian approach, he is the same person, Euler, who also given equation for the finding out forces involved in fluid element moving in streamlined flow. Euler's equation of one-dimensional fluid flow, fluid motion, one-dimensional fluid motion. So this Euler's equation, for Euler's equation, we will let us draw fluid element. This is a fluid element. Cylindrical fluid element we are taking for our simplicity. This is a cylindrical fluid element, and this is streamline. This is streamline like this. This is streamline, and this is streamline. Area of the cylindrical element is dA. At this point, pressure is acting at this point P dA. Because length here, length of fluid element is we are taking D as a length of fluid element. So pressure at this point of surrounding fluid. On this element, pressure from surrounding fluid is acting P into D, and at this time ds, this pressure become P plus dP into dA. Because this fluid element is moving along this direction with velocity u. So surrounding fluid is exerting frictional resistance. So frictional resistance will be Fs. This is a frictional resistance force Fs, and also weight of the fluid element W. And if you join this one, it is theta. So W is the weight of fluid element. And one thing I also defined here, dP, that is a perimeter of fluid element. Perimeter of the fluid element. This perimeter, circumferential perimeter, and ds is length, and here we will also define length y direction. This is a height of the fluid element, dy, vertical height, means here y x direction and y directions, we are taking distance along y direction. So we know that this angle is theta, so this angle is 90 minus, this angle will be theta also. This angle is theta, this is it, angle theta, and this is 90 minus theta, so this is theta. So dy equal to ds sine theta. Here dy equal to ds sine theta. You can see from the diagram, dy equal to ds sine theta, and here one component is acting, that is W sine theta. W sine theta is this component acting downward along the fluid element. So now applying force balance equation for this motion of the fluid element along this fluid element moving along the direction. So we apply force balance equation. Let us make it simple, smaller size. Applying force balance equation. So that is PdA. This force is PdA minus P plus dP into dA, and minus W sine theta, and minus tau shear force acting due to surrounding fluid offering resistance to moving fluid element on dP on whole surface. Circumference multiplied by 2 pi r. You know that circumference of the cylindrical element is 2 pi RL. So 2 pi r equal to dP and L equal to ds, equal to acceleration of fluid element, mass into acceleration. So mass equal to rho g, mass into volume, dA ds, mass into volume into acceleration. Acceleration is as. Now putting value of W sine theta, so now this will be equal to minus P minus dP into dA, and minus W equal to rho G dA ds volume into density into G W into sine theta minus tau dp ds equal to as rho dA ds. Here one thing that sine theta w ds sine theta equal to ds sine theta equal to dy. Putting here minus dp dA minus rho g dA dy minus tau dp ds equal to as. But one thing that I want to define here, as acceleration of this fluid element. We know that u is a function of, because this fluid element moving with velocity u, and u is a function of displacement s and t. So exact differential du equal to del u over del s ds plus del u over del t dt. Dividing whole equation by dt. So du over dt equal to del u over del s ds by dt plus del u over del t. Considering fluid, because we are considering that this motion of fluid element is steady. When motion of fluid element is steady, then this term becomes 0, and this term equal to acceleration. As equal to del u over del s and del s over del t, del s over del t equal to u, that is equal to u del u over del s. Putting value of as in this equation equal to u, and we can write del u over del s equal to, you can also write u du over ds, because there is a single variable u is varying with respect to only s, so we can write del u over del s equal to du over ds for our simplicity and calculation. So u du over ds into rho into dA into ds. So ds will be replaced, equation will be reduced to u du rho dA. So writing this equation like u du rho u du dA rho du u du dA, okay, and plus dp dA and plus rho g dA dy equal to, we are changing side, tau dp ds. So now erasing this one, erasing this part, rho u, dividing whole equation, dividing whole equation by dA ds and rho. dA ds rho, dividing whole equation by dA ds rho, so we get u del u over del s plus dp 1 by rho dp over ds plus rho g, rho will be eliminated, that will equal to g dy over ds equal to tau upon rho dp over dA. That is equation. This is a final equation, and this sign will be negative. So now there are different terms in this equation. Now writing properly again here in proper format. Once again I write u del u over del s plus 1 by rho del p over del s plus g dy by ds equal to minus tau upon rho dp over dA. This is final equation of Euler's equation of force. So what are different terms 1, 2, 3 and 4? So one term number 1 denote this is a you see change of velocity. It is also known as a kinetic acceleration, because you can say force acting per unit mass. This is a force acting per unit mass due to convection, because u changing del u over ds, u changing with respect to position. So this is a convective acceleration. This term 1 is a convective acceleration. Term 1 is a convective acceleration. Term 1 is a convective acceleration. 1. Convective acceleration. Or you can say force acting per unit mass due to change in velocity with respect to space, and term second. You see term second. Change of pressure with respect to space. It is a force acting due to change of pressure per unit mass. Force acting due to change of pressure and per unit mass. And term second. It is again force acting per unit mass. Term third, force acting per unit mass due to gravitational pull, due to gravitational acceleration. Force acting per unit mass due to gravitational acceleration. Force per unit mass due to gravity. And what is term 4 stand? What term 4 interpret? If it is force acting per unit mass due to frictional resistance offered by the surrounding fluid over the movement of the fluid element, cylindrical fluid element. This is a term 4 frictional force acting per unit mass. Frictional force acting per unit mass. So this is a physical interpretation of one-dimensional Euler's equation of force acting on the fluid element. If there is an ideal fluid, what will happen if fluid is ideal? If flow is ideal means fluid become inviscid, viscousness. There is no viscosity of the fluid. There is no any friction resistance, so this term will become zero. And equation will be reduced only u del u over del s plus 1 by rho del p over del s and plus g dy by ds equal to 0. This is a simplified equation when there is no any viscosity present in the fluid. So this is a general equation. We have derived. This is a general equation that is a u del u over del s plus 1 upon rho del p over del s ds plus g dy over ds equal to 0. Because ds is a common everywhere. Del s is common. These are del s, not ds. Please read it as a del s. So multiplying whole equation with del s, you get u del u plus dp over rho plus g dy equal to 0. This equation you can further write like this: u del u 1 by 2 d u square plus dp by rho plus g dy equal to 0. This you can say final equation of the one-dimensional fluid element motion, forces acting on the one-dimensional fluid element motion of cylindrical kind, but the fluid is a ideal fluid, no viscosity present. And if this equation, because now we want to integrate this equation along the whole of the path. When force is integrated with along the path f into dx, f multiplied by distance. When we integrate along the path, then it becomes energy because the work is being done. Because this fluid force is acting on this fluid element and fluid element moving from whole of the path. So work is being done. So how much work done? We integrate this equation for whole of the path. So integrating this equation for whole of the path, what we will get? Integration dp by rho plus integration 1 by 2 du square and plus g integration dy equal to integration of the 0. So here again fluid is incompressible. Then we can take rho as a constant. So 1 by rho integration of dp will be p, that is a p plus 1 by 2 u square plus gy equal to constant. This is equation of Bernoulli equation. And this is how we derived Bernoulli equation for one-dimensional fluid motion. We can further write here p upon rho plus u square upon 2 plus gy equal to constant. Dividing whole equation by g, so p upon rho g plus u square upon 2g plus y equal to again constant, because constant when divided by another constant it is remains constant. You can write it like Vog equal to specific weight W gamma u square upon 2g plus y equal to constant. So this is a pressure energy head, this is a velocity energy head, this is a position head. So we can represent all these terms energy heads with the energy hydraulic energy line, total energy line. So let us define these heads. This is a Bernoulli equation. This is a Bernoulli equation, Bernoulli's equation for one-dimensional STD incompressible inviscid flow. Conditions are there: one-dimensional, incompressible, inviscid and ideal flow. Conditions क्या हैं? One-dimensional. Number 2, ideal fluid, no viscosity. Number 3, incompressible. Number 4, inviscid. Inviscid already है. One-dimensional, ideal, incompressible and steady flow. STD. 4 conditions are there. 4 important conditions are there. There are 4 conditions always sometimes asked in competitive examination. So how we represent these heads? By using hydraulic energy line. So let us draw hydraulic energy line. Let us take a datum. This is a datum. This is a total energy line. And positions are there. Datum line, and position at here is a Z1. Here position is Z2, and here position is, suppose here we are taking Z3. At different positions we are measuring fluid. So let us here we draw hydraulic grade line. Velocity is increasing because change of the like this. This is a like this. So here from this point to this point, this is a pressure. P1 upon gamma. From here that will be equal to P2 upon gamma. Here pressure is changing. This one is a P3 upon gamma. And here total energy line will be like this because frictional loss will be there. So this one is a V1 square upon 2g. From here to here P2 square upon 2g. Kinetic energy head here V3 square upon 2g. Actually this is a total energy line, ideal के लिए for ideal, and this is a total energy line real, because when fluid will flow across the conduit or pipe of varying cross section to energy losses against friction, the velocity will continuously, this energy line will continuously decrease. This is a hydraulic grade line. This one is known as HGL, hydraulic grade line. So it is varying due to cross section of this conduit. This flow channel is changing, and you see that when cross section is decreasing, velocity is increasing. That's why velocity head is increasing. From here to here you see velocity head is increasing, but here again cross section is increasing, so velocity head is decreasing, almost remaining constant, and this line is dropping because of frictional loss. So here position head plus pressure head plus velocity head, all 3 heads remains constant. For ideal, this will be ideal line and this will be actual line. So this is all about Bernoulli theorem, and this is a very, very important theorem. In dynamics of fluid, everywhere Bernoulli theorem applies. So many applications of fluids, whether flow of the helicopter or ship in a sea, or flight of the aeroplane. So many applications you can describe by using any kind of flow problem where energy is involved. You can use Bernoulli theorem. So this discussion is very, very useful. That will also explain what is a hydraulic grade line and what is a total energy line. Why total energy line is sloping downward. It is important here. That is very important for a competition point of view. You will always get question from Bernoulli equations, all 4 kinds of Bernoulli equations. So I think please like and subscribe and share it to your friends, and Thank you very much for watching my this video lecture, and have a nice day.